Welcome. In this video, we're going to discuss the main takeaways from atomic theory and how we can use that to understand the atom in the periodic table for an introductory college chemistry class. So, the main takeaways that we have to recognize from atomic theory is that atoms generally contain three subatomic particles. They have protons, they have neutrons, and they have electrons. Protons have an overall charge of +1. Neutrons are neutral. They have a charge of 0. They have no charge. And electrons have a charge of -1. So we can say that protons and electrons have equal but opposite charges. Equal because they're both 1 respectively, but they're opposite in that one's positive, one's negative. The next thing we have to recognize is that protons, neutrons, and electrons are not the same size, which is important. If we were to think of proportions to size, protons and neutrons are very similar in both size and mass. However, when you compare electrons to those, they are extremely small. In fact, it's about 1/2000th, give or take, again, 1 in 1,836, so very, very tiny compared to that of a proton or neutron. However, keep in mind, the charge is still equal. So just because it's a lot smaller, it just means it's packing a big punch. And last but not least, protons and neutrons are in the center of the atom, aka in the nucleus, whereas the electrons occupy the free space surrounding the nucleus. So again, we don't really want to think about it in terms of them orbiting, because that's not the case. They move very randomly and they move very quickly around the nucleus, so we can't at any given point in time identify, exactly where an electron is with knowing the certainty of how fast it's traveling. So something to kind of keep in mind there. So let's discuss how we can use these ideas of subatomic particles to actually do some chemistry and have an understanding as to, essentially what's going on inside the atom. So there's two main values that we have to take away from this that we really are going to see a lot in chemistry problems. The first thing we have to know is the atomic number, which is commonly represented by this capital Z here. It's like a variable that basically represents atomic number. Keep in mind, the atomic number is what gives an element its identity. So for example, hydrogen. In order for hydrogen to be considered hydrogen, it has to have 1 proton, aka it has an atomic number of 1. In order for helium to be considered helium, it must have 2 protons. Again, the identity is only related to the atomic number, which is the number of protons in the nucleus. So the number of electrons has no indication as to what the atom is. The number of neutrons does not give us any indication as to what the atom is. Keep in mind that when we're deducing the atomic number, it must be a whole number. You can't have a half, a quarter, or a third of a proton. And if you look at a periodic table, so let's say we were to look at hydrogen here, for example, there's going to be a little number 1 on top. That's our atomic number, okay? Now again, this is if we're looking at the periodic table here, because there's other ways you can represent atoms with isotopic notation, which I'm going to get into in a little bit, where it's not necessarily going to be on top, it's going to be someplace else. The next important number we have to know is referred to as the mass number, which in this case is commonly abbreviated as the letter A. I know it seems kind of odd, but it's A and it's Z. Now what the mass number is it's the sum of the protons and the neutrons combined. So if you take your number of protons, you take your number of neutrons, you're going to combine those together. That is going to get your mass number. Now when you write out isotopes, you usually write the name of the element, like carbon, oxygen, hydrogen, etc., put a hyphen here, and then put that mass number A. Because with this, we can deduce the number of neutrons very quickly, because we know that carbon is determined to be carbon based on the atomic number. So all of these have 6 protons. However, if you take 6 and subtract it from these mass numbers, you'll get that number of protons. So here we have 6 neutrons, we have 7 neutrons, and we have 8 neutrons. So this is how we determine an isotope. Now, You might see carbon-14 represented like this. You might see a C like this, and then you might see a number 14 here in the upper left-hand corner. So here's usually how you see isotope notation. Let's say X is the element, then you put your mass number on top, and you put your atomic number here on the bottom. So it's mass number over atomic number. So if you think about how this would work here, it would be 14C, and then sometimes people will put a 6 here. Now, you don't have to put that Z value there. You don't have to put that atomic number there, because it's known, it's understood, that if I were to give you an element like oxygen, for example, no matter what oxygen I have, I know this bottom number is going to be 8, because it's the number of protons. I can get that from the periodic table. So they don't have to put this here. Instead, they could just put, for example, O16, and that's like a common thing that you could see there. Okay, so isotopic notation, it's always mass number over atomic number, and then commonly in the upper right-hand corner here, you'll put the charge, which I'll label as a C. Okay, so for charge, if an atom is neutral, that means they have equal amounts of protons and electrons. So if this had a charge of 0 here, there's no charge, it's just not listed, that means that this atom of carbon has 6 protons and it has 6 electrons, because in this case it's neutral. But let's say we put a 2- here at the upper right hand corner of oxygen. I know that oxygen, remember what, has to have 8 protons, so then how many electrons does it have to have? It would have to have 10 total electrons. Why? Because if I have 8 positive things and I have 10 negative things, because remember, electrons have a negative charge, protons have a positive charge. Do you see how if I combine these two values here, overall I have a -2 or a 2-. I have 2 more negative things than I have positive things. That's where we get that charge from there. Now, when you have a charge, so let's say O2- is a good example. Another one is Na+, which is basically your sodium ion. You have what's called an ion. So if you have a charge in the upper right-hand corner, you have an ion. If your ion is negative in charge, it's an anion, which is a negative ion. Anion, a negative ion. Again, they have to gain electrons for this to happen. You don't lose protons or gain protons to become an ion. Your protons are staying the same because it has to still be oxygen, right? You're either gaining electrons to be negative, or you're losing electrons to be positive. So when you lose electrons to become positive, you have cations. And again, you have a T here. T looks like a plus sign. A cation. They're positive, right? Like a cat paws. Positive. I know you guys love that. So cations are positive, anions are negative. How are they different? One of them gains electrons to become negative. So we gain electrons to become an anion, and we lose electrons to become a cation. Now let's look at the periodic table, and let's see how we can use some of this stuff. A couple things to keep in mind about the periodic table. Most of the periodic table are metals. So if you look at the periodic table, I don't know exactly what the percentage is, but most of the ones that we see here are considered metals. Okay. Couple things to keep in mind that are not listed here. We often have a staircase that's drawn right here, which basically separates our metals from our non-metals, and they basically kind of show us where our metalloids are. So metalloids are usually things that border the staircase. So we have boron, which is a metalloid. Aluminum is a metal that's bordering the staircase, but it's one of the examples where that's not the case. Silicon, germanium, arsenic, antimony, tellurium, and astatine. These are all of your metalloids. Polonium is not considered a metalloid. So we have metalloids here. Everything to the left of this, as a general rule, are going to be metals. Everything to the right are going to be your non-metals, and they all have different properties. Now, when you think of ions being formed, it's usually by their ability to gain or lose electrons. So if you have an ion that exists in group 1, for example, these typically are going to have a charge of +1. Hydrogen, they like to form +1s a lot too. So all of these are going to be +1s. These right here tend to be +2s. These here tend to vary. in their charge. But what's unique about a lot of these is that's where you have your Roman numerals that come in, which we'll get into in a future video, which we'll get into that later. That kind of gives you a hint as to what type of ion it forms. You get to your metals here, like aluminum. These typically tend to be +3. These generally don't tend to form ions like carbon and silicon, germanium. These, right here, we have metalloids, and we have a very, carbon doesn't really like to bond ionically. It's more of a covalent thing. And then tin and lead, those are going to form metals as well, but they follow the same rule as your transition metals here. Then for your nitrogen here, these tend to be 3-. So nitrogen and phosphorus tend to be 3-. These tend to be 2-, 1-, and then these not really form ions because, again, they're noble gases. They are deemed to be inert, which means they don't really react. So, as a general rule, +1 cations, +2 cations, aluminum, +3 cation. These two, 3- or -3, 2-, 1-, and then no charge. They're generally pretty neutral and they don't like to form ions. So, that's going to wrap up this video. Thanks for tuning in.